Okay, so problem number one here, it looks like an exponential problem. We're going to try and write that as a logarithm to solve it. So the log, where's this up? The log of base 3 of 81 is 2x. So I'm going to find what log of base 3 of 81 is with my either log base or the way of log of 81 divided by log of 3. And then it looks like I'm going to have to take that answer and divide it by 2. So log of 81, if I do the old calculator here, divided by log of 3 divided by 2 is 2. Number 2 is log, actually it's a natural log. Because of being base e, it's natural log. And I'm not going to write it, I'll write it for a moment, but it's implied to be base e, but you'll never see that. So it's natural log of 12 equals negative 0.0097t. And we would want to find the natural log of 12 and then divide it by negative 0.0097. So if we enter that in our calculator, the natural log of 12, I just tend to push enter and find that first, and then divide by negative 0.0097, I get negative 256.1759. Number 3 is an exponential problem. We'll turn it into a logarithm. Log base 3 of 79.6 is x. And so I'm going to just do the log of 79.6 on this old calculator and divide it by the log of 3. And if you use log base, you get the same thing. It should be 3.984. Number 4 is kind of a lengthy problem. You want to first put a couple of logarithms together into a single logarithm, the natural log, and in order to put two logarithms that are added together, you FOIL the arguments, or you multiply the arguments. So it would be 21x plus 35 minus 3x squared minus 5x equals the natural log of 24x. Now, in order for two logarithms on each side to be equal to each other, you want to kind of ignore the logarithms and just compare the arguments. So the fact, and I'm going to write this left one a little bit cleaned up. It'd be negative 3x squared. 21x minus 5x would be plus 16x plus 35 equals 24x. I want everything on one side to be 0, but I also at the same time would like my dominant term, my lead term, to be positive. So I'm going to take this entire side over that way. So 0 equals 3x squared. Subtracting 16 from 24x would be 8x minus 35. Okay, and then simply factoring can lead us to the answers. 3x and 1x. And factors of 35 that make help make 8, well, with that 3 being there, it's probably 5 here and 7 here, because 15 and 7 makes 8. 15 and 7 would make 8 only if the 15 was positive and the 7 was negative. And now we can say the answers are negative 5, and solving this guy right here would require us to add 7 and divide by 3, so I think the other answer is 7/3. Now negative 5 is not one of the solutions actually, because it ends up making this argument and this argument negative. And what we know about a logarithm is that the argument must always be a positive. So we're going to discard the negative 5 and settle on the answer being 7/3. Okay, on number 5 here, we're going to put together the two logarithms into a single logarithm. So it'd be log of 7 minus x over 3x plus 2 equaling 1. And then I'm going to turn this into an exponential. So 10 to the first equals 7 minus x over 3x plus 2. I'll multiply both sides by the denominator 3x plus 2. And that will be 30x plus 20 equaling 7 minus x. If I just move the x's to one side, numbers to the other, I would then have 31x equaling negative 13. And I'll divide by 31 to get x to be negative 13 31st. Now I'm just going to tell you that on number 6 we are going to run into problems here, and it's okay. It is what it happens. So let's put those together into a single logarithm. Logarithm of x squared plus 3x equals 1. Let's write it as an exponential. E to the first equals x squared plus 3x. Let's minus e and get 0 to be x squared plus 3x minus e. Now you're going to run into problems here because e doesn't factor. You just can't. You could take this to the quadratic formula where a is 1, b is 3, and c is negative e, but most people don't like that. So instead, we're going to graph this and find the zeros. Now, I'm heading to my calculator to graph the natural log of x plus the natural log of x plus 3, and most importantly here, I need it to be equal to 0, not 1, so minus 1, and then I'm going to find the zeros. I'll take a picture of my calculator and put it on here and show you the answer from it. Okay, so I ran through the process of finding the zeros, being left bound, right bound, and guess, and the zero of this problem is 0.729. So that is our solution to this equation. Number 7 is a logarithm, so what solves it is most likely an exponential. Let's take e to the second equals x. So e to the second is 7.389. Number 8, let's get the exponential portion alone. So our goal is to get this by itself. And what I'll do there is I'll add 6. 5e to the x equals 53. I still want e to the x alone, so I'm going to divide by 5. I now have e to the x equals 53 fifths. And I want to turn that into a logarithm to find the answer for x. So the natural log of 53 fifths is e. And the natural log of 53 fifths is 2.361. Okay, number 9 has the solver written all over it to me, so I'm just going to type this into my solver and I'll take a picture of it for you. Okay, so there's a picture of what my solver looks like with that equation in there. Basically, remember, you move the entire right side to the left side by subtracting and containing the entire right side in parentheses. So when I go to solve it, it says I arrow down, I have a y and a t variable. It says how many people or how many days will 900 people be affected. The y is the total number of people, so make y 900 and solve for t. And the answer is 12.99, so about 13 days. Okay? And then problem number 10 says for problem number 9, how many people will be infected in 22 days? We'll make t 22 and then alpha solve for the number of people, and that's right at about 1,000. Okay, number 11, let's get the logarithm portion of this problem alone by dividing by 3. That gets the natural log of 4x all by itself. And then let's spin that into an exponential. So e raised to the 5/3 equals 4x. Now I'll take one last step to get x by itself, and that is divide by 4. So e to the 5/3, then divided by 4. To about 3 decimals would be 1.324. Number 12 is an exponential, so we're going to use a logarithm to solve it. Log with a base of 3 of 19 equals 2x. I'll have to find log base 3 of 19 and then divide that entire thing by 2. And that answer to about 3 decimal places is 1.340. There really isn't anything too complicated or fancy going on in 13. It's just making sure we enter this carefully in our calculator. So on the home screen, I just would literally type 5.1 times 1.32 raised to the square root of 2. And so literally just what I see. And the answer is, to 3 decimal places, 7.552. No tricks. Okay, number 14, you might make this more complicated than it is, or do some things in a different way than I did. But since it just says find the answer, I want to be very careful that I just enter this into my calculator like I see it. So I'm going to say, well, we want to take 2 natural log of 7. Well, the natural log is going to come with an open parenthesis, so I better close that, and then close that for that entire top. And then I'm going to say divided by, and I better start a parenthesis and say 3 natural log of 5 minus 5 natural log of 6. Close that twice because we have one open over here. Okay, so if you type that just like that on your calculator, you should be able to get the answer there. 2 natural log of 7 divided by 3 natural log of 5 minus 5 natural log of 6. And the answer to about 3 decimal places would be negative 0.942. All right, on number 15, this one's simple enough to just put the 3 in and then just work it out. So it's got 300 divided by parentheses 1 plus e to the negative, well, I'm just going to say it's negative 6 because negative 2 times 3 is negative 6. So that'd probably be the easiest way to do this one. 300 divided by 1 plus e to the negative 6th. To 3 decimal places would be 299.258. Okay. We know that this, I think we know that this 2 we see in front is really supposed to be at the end, so it's more likely f of x equals negative e to the x plus 2. The reason I put that there is that 2 drives the asymptote up and down, and the asymptote that a exponential function has is a horizontal asymptote. So here's what I know so far. I know so far that the horizontal asymptote hits at 2, and when I graph this guy, he has a reflection, and so I'll make a quick sketch of what my calculator looks like. Hey, looks something like this going on down here, something like that, roughly. Okay, maybe a little bit exaggerated, but roughly. What I really want to point out is that a horizontal asymptote does not get in the way of domain going from left to right. So that is, the domain of all things exponential will be negative infinity to infinity. Absolutely. Didn't even need to know anything other than the fact that this is an exponential function. Okay? The range, on the other hand, this horizontal asymptote is a barrier for range because we look at range from going bottom to top. Now what I know is the graph will either be below the asymptote or above it. Since I graphed it on my calculator and found it to be below, my range is from negative infinity to 2. Now 18 is a pretty simple question, but it also can be one that if you're overthinking it, is not easy. The natural log of 3.76, somebody might think, I got to turn that into an exponential. It's not. Just find the natural log of 3.6. So natural log 3.76. The natural log of 3.76 is 1.324. So don't overthink that one. Just punch that in the calculator and you're good to go. All right, the natural log of the square root of 18 is just simply the calculator, the natural log of the square root of 18. And so the answer is 1.445. Number 20, write 3 to the 5th equals 243 in log form. So remember, log with a base of 3, and we're trying to get 3 to become 243. And what will get us from 3 to 243 is an exponent of 5. So just remember that the answer to a log problem is always the exponent of the exponential. With that in mind, 21 says write the log base 7 of b equals 12 in exponential form. So the base is 7, the exponent is the 12, and the answer of 7 to the 12th would be what b is. So 7 to the 12th is b, is a. Number 22 says find the domain of the function. So the domain might be affected by the asymptote. So that's where I'm going to start my thoughts. What type of asymptote do all logs have? All logs have a vertical asymptote. Where do vertical lines get moved? Left and right. Where is this one? At x equals 1. So with that in mind, there's a vertical asymptote at 1. Okay? The graph is either going to be on the right of it or on the left of it. So you could graph this to find that out. And I have, and the graph is to the right. So what's the domain? The domain is from 1 to infinity. Now, I'm not a great big fan of this 2 out in front here. It really belongs at the end, but I kind of know why they do that. We want to be careful that we understand this is the natural log of x, then plus 2. Okay? It's not the natural log of x plus 2 in parentheses. So a vertical asymptote is what all logarithms have. You move a vertical line according to left and right. And left and right happens inside parentheses. What's in there? Nothing. So the vertical asymptote is at 0. What is a vertical line? X equals 0 is a vertical line. Finding the vertical asymptote on 24, the vertical asymptote can only be moved left and right. So this moves the graph left and right. So the vertical asymptote must be at, remember, against intuition inside parentheses, so it's x equals negative 3. Okay, so we're going to find the domain, asymptote, and intercepts of this graph. In order to do that, I'm going to start this discussion at asymptotes. Okay, I think everything kind of plays off of that. So the asymptotes of a natural log or of any log problem is a vertical asymptote. And a vertical asymptote happens where it's moved left or right. So this has a vertical asymptote at x equals negative 2. And we can kind of see that on my graph over here at x equals negative 2, and I kind of missed it. That's the value the graph gets closer to and closer to. So what's the domain? I think the domain is from -2 to infinity. It doesn't say what is the range, but it would be worthy of noting that that graph does not stop. That graph continues to go down, 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 down. Okay? So the range would be -infinity to infinity. Okay? Now for the intercepts. To find the x-intercept, we'll let y be 0. And now solve this. Well, when you're looking at a log problem and you're kind of stuck, you gotta turn it into an exponential. So e to the 0 equals x plus 2. If I subtract 2 from e to the 0, well, e to the 0 is 1. So 1 minus 2 is -1. So the x-intercept is -1, 0. Now the y-intercept, as we've done since day 1 of pre-calc, is let x be 0. So this would read something like y equals, or f of x equals, the natural log of 0 plus 2, or it'd just simply be the natural log of 2, which the natural log of 2 is 0.693. So the y-intercept is 0, 0.693. Okay, so I've graphed the natural log of x minus 2, and what we know about natural log is that they have a vertical asymptote. Any logarithm has a vertical asymptote, I should say, and it's at x equals 2. And that means that the domain, as we can see from the graph even over here, the domain is from 2 to infinity. And the x-intercept can be found by letting y be 0, and turning that into an exponential. So e to the 0 equals x minus 2, e to the 0 plus 2. 1 plus 2 is 3. So the x-intercept is 3, 0. There isn't any reason to waste our time trying to find the y-intercept, because as we see from the graph over here, this wall is going to keep the graph from hitting the y-axis. So there isn't a y-intercept. Okay, so I've taken my picture of my calculator screen, and actually this is kind of two screens pieced together, so if it looks kind of funny, that's why. If you have log base, you can just enter it like you see it. If you don't have log base, you got to do log of the top over log of the base. So log of x plus 2 divided by log of 3. And both of these, depending on which one you use, make the graph over here, okay? Now what we know from this is that there is a vertical asymptote, and I know this because all logarithms have a vertical asymptote. And that vertical asymptote is actually happening right at -2. And I know that because it's against what I expect in parentheses. A graph's been moved left, okay? So the domain of this guy is from -2 to infinity. And the intercepts, well, we would want to follow the plan for x-intercepts. And that plan would be to let y be 0. And then as you stare at a log problem wondering what the answer is, we turn it into an exponential. So 3 to the 0 equals x plus 2. 3 to the 0 is 1. 1 equals x plus 2. Subtract 2, and we should find the x-intercept at -1. So that's that. Now the y-intercept we find by letting x be 0. So y equals log base 3 of 0 plus 2, or just go find log base 3 of 2. Log base 3 of 2 is 1.585. So our y-intercept is 0, 1.585. Okay, number 28 is an exponential problem, and all exponentials have a horizontal asymptote. Horizontal lines are moved left and right. No, they're already there. Horizontal lines are moved up and down. And we move things up and down based on what's on the end of the equation. Since there is nothing on the end of that equation, the horizontal asymptote is at y equals 0. Okay, made a quick sketch of what my calculator is going to look like here for this one. Just a rough sketch. Basically, don't waste your time finding the x-intercept, because that's y equals 0 is the horizontal asymptote. The graph will get closer and closer to the x-axis, but it won't ever hit it. So if you go searching for that, you're going to be wasting some time there. There isn't one on this one. And the y-intercept we can simply get by letting x equal 0. So 4 to the 0 minus 1 would be 4 to the negative 1, which means 1/4. Because remember, negative exponents don't change the positive or negative side of the number. A negative exponent just simply means that guy should be on the bottom with a positive exponent. So y equals 1/4 is the y-intercept. Okay, so since number 29 is an exponential function, we will have a horizontal asymptote. And the horizontal asymptote will be y equals, and we move a horizontal line up and down, and that happens outside of parentheses out here on the end. Since there's nothing there, the horizontal asymptote is at 0, which means it's the x-axis. The graph will get closer and closer to that as we go to the left, and therefore the x-intercept doesn't exist. The y-intercept, however, can be found by letting x equal 0 and getting 2 to the 3rd, or 8. So the y-intercept is at 0, 8. Okay, 30 is also a exponential function. So since it's an exponential function, it has a horizontal asymptote. And it has a horizontal asymptote at -5. And we can envision that that graph would then have a horizontal asymptote. The graph will go up from there. So we want to find the intercepts. Let's find the y-intercept by letting x be 0. Which results in 2 to the 3rd minus 5, which results in 8 minus 5, which results in 3. So the y-intercept is at 0, 3. And the x-intercept, we let y be 0. 0 equals 2 to the x plus 3 minus 5. To solve an exponential equation, you first want to get the exponential part by himself. So 5 equals 2 to the x plus 3. And then you want to turn that into a logarithm. So log base 2 of 5. is x plus 3. And then at the very last step, we'll subtract 3. And log base 2 of 5 is 2.3219. Subtract 3 is negative 0.678. And so the y-intercept is negative 0.678, comma 0. Okay, to find the range of this graph, probably starts with first identifying what type of asymptote it has and where it's at. So since it's an exponential function, it has a horizontal asymptote at y equals negative 5. And the parent function of exponentials kind of looks like this. So if we just took that whole graph up 5, or excuse me, down 5, it's going to look like this. So what is the I guess we should have a horizontal asymptote there. What is the range? Well, the graph starts at negative 5 and goes up towards infinity. So negative 5 to infinity. The domain on 32, the domain of an exponential function, since an exponential function has a horizontal asymptote, a horizontal line will not stop you at all from going left to right. So the domain of any exponential function is negative infinity to infinity. Number 33, the domain of a logarithmic function. Well, first let's investigate where the vertical asymptote happens. The vertical asymptote happens at 6. So there's a vertical line at 6, and the graph of a logarithm, unless he's reflected, will go onward to the right. So the domain of this logarithm is 6 to infinity. Number 34, find this. I'm going to start with asymptotes because he helps me figure out everything else. And it's not really asymptotes, it's just find the asymptote. Since it is an exponential function, it has a horizontal asymptote. And that horizontal asymptote is y equals, the graph moved down 3, y equals negative 3. Okay? Now, that means that the graph is going to look something like this. There's my horizontal asymptote. The graph will go up as you go to the right. Okay? So what we know is that the range is from negative 3 to infinity. And the intercepts, we can find the x-intercept by letting y be 0. I'd add 3. And now I have the exponential alone, and what solves an exponential is a logarithm. So log base 2 of 3 is the exponent x minus 1. I'll find out what log base 2 of 3 is with my calculator, and then I'll just simply add 1. $1.58496 plus 1 is 2.585. So the x-intercept is 2.585, comma 0. The y-intercept, we want to let x equal 0. So I'll just scoot this over and find it. The y-intercept, let's let x equal 0. So it amounts to 2 to the negative first minus 3. 2 to the negative first is a half, minus 3 is equal to negative 2.5. So 0, comma, negative 2.5. I'm going going to start this question 35 by finding the asymptote, even though that's not the first thing. That leads me to everything else. So the asymptote of a log problem is a vertical asymptote. And a vertical asymptote, a vertical line can be moved left or right, which happens inside parentheses. So this guy happens at x equals -1. That means that the graph's going to look something like this. And a logarithm's parent function kind of just looks like that in general. If there's a reflection, you got to be concerned about that. But we have no negatives involved here, so he's just up and as you go to the right, kind of like so. You can also graph that and see that. That's no big deal. So the domain is -1 to infinity. And the x-intercept we can get by letting y be 0. And when I'm looking at a log problem trying to solve that, I might turn it into an exponential. So e to the 0 equals x plus 1 minus 1. Well, e to the 0 is 1, minus 1 is 0. So it's x equals 0. Okay? And if you think about that, the ordered pair 0, 0 is the origin, and therefore it is also the y-intercept as well. So that's both intercepts. Okay, so on 36, I notice it's a log problem which has an asymptote of vertical asymptote of x equals 3. That would kind of tell me that over here at 3 there's a vertical line, and the logarithm will tend to go to the right unless there's a reflection again, but it'll go up and to the right, and that means the domain is from 3 to infinity. And the x-intercept, we can tell from our graph that there's not going to be a y-intercept, okay, because this can't get over there to hit it. We can also find the x-intercept by letting y be 0. And turning this into an exponential to solve it. 2 to the 0 equals x minus 3. 2 to the 0 is 1. Adding 3 is 4. So the y-intercept is 4, 0. Actually, that's the x-intercept. Misspoke. Okay, so we're gonna find the asymptote first. Since this is a exponential, it has a horizontal asymptote, and the horizontal asymptote is y equals -3, and that would be kind of looking like right here. And I know that the parent function kind of exponentials kind of looks like so. It just kind of goes up and to the right as you go on. So you can graph this and see that as well. If we're looking for the range then would be from 3 to infinity. And the intercepts can be found by letting x be 0. So it's 2 minus 3 is -1. So 0, -1. And the other intercept can be found by letting y be 0. And if we let y be 0, we would add 3. And now when I have an exponential and I'm stuck, I'm just going to turn it into a logarithm. So log base 2 of 3 is equal to x plus 1. And now subtract 1. So log base 2 of 3 subtract 1 is 0.585. So the range of an exponential here I'm going to consider what the asymptote is. An exponential function has a horizontal asymptote, and it would happen at 3. So my graph has a horizontal line here. Now what we don't know is the graph on the top or the bottom of that line. So you might, and I see a reflection with that negative on the front of the e, so you might just take a moment and graph negative e to the 0.6x plus 3, and you'll see that it is kind of, the graph kind of does this number here. Okay, so the range is what? The range is from negative infinity to 3 when you start looking at it this way. On number 39, we only want the x-intercept, and to find the x-intercept, we let y be 0. And take the algebra steps necessary to get x by itself. Divide by negative 1. So 3 is equal to e to the 0.6x. And now it's right here that I am staring at a log, I'm staring at an exponential, and a logarithm will solve that. Specifically, since my base is e, I'm going to use natural log. The base is implied to be e, so the natural log of 3 is equal to 0.6x. Let's divide by 0.6. So the natural log of 3, then divide by 0.6. Make sure you close your parenthesis on that 3. That is 1.83, comma 0. Okay, find the vertical asymptote. Okay, logarithms do have a vertical asymptote. Vertical lines are x equals, and vertical lines, we can only move them left and right, which happens right here. So it's going to be at negative 4. Remember, it's opposite of what you think when you're inside parentheses. So the vertical asymptote doesn't happen at power 4, but rather negative 4. There isn't a whole lot to show on this whole page. I'm going to go to my calculator, and I'm just going to go to Stat and Edit and enter the x's in list 1 and the y's in list 2. And we've done this enough, I don't think you need to see this, but 0, 1, 2, 3, and 4 go in list 1, and 4, 5, 6, 8, and 12 go in list 2. And then once I've got those entered, this says find an exponential model. So I'm going to go Stat Calc, and then I'm going to go down on my calculator. The exponential model is 0. It says EXP regression. So go to 0, push enter, 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 enter until you get to calculate, push enter. Now, the model that it gives me is y equals a times b to the x. Okay? And so what we're going to do is we're going to write that. We're going to write that with the numbers that it told me. Y equals, I'm going to go about 3 decimal places. 3.807 times 1.306 raised to the x. This is the model. On 42, we want to find the logarithmic model. Now, don't get that confused with the logistic model. The model you're looking for to do logarithms is the natural log regression. Okay? So when I go there, it says the model is y equals a plus b times the natural log of x. Only we know what a and b are after we put the numbers in. It tells me that my calculator says the y equals 2.083 plus 1.257 and natural log of x. Now, don't add those. I know in the past I've had a few people always get tempted to add these numbers together. Remember, multiplication takes over before you can do the addition. So you aren't making it simpler by adding those together. We must leave it just like that. Okay, so stat edit, put the data in, X is in list 1, Y is in list 2. Stat calc log regression, which is the natural log regression. And we write, as what the calculator says, is Y equals 9.934 plus, actually in this case it's minus 4.227 natural log of X. And that is the line that, or I should say the equation that fits the data the best. Okay, so we're going to put the data into the calculator under stat and edit, and then stat and calc exponential regression, and we get Y equals 8.063 times 0.793 raised to the X. So that is the model that fits this data the best. Okay, so we have to decide which of these, linear, exponential, or logarithmic, fits the data the best. Some people can look at numbers and kind of see the pattern. If it's equal steps, that's linear. If it's kind of exponential growth, it'll grow more and more and more over time. But no real need for that. Just put the data in your calculator and then do stat calc. Start with linear regression and look at the r squared. The linear r squared is 0.935, and then find the other one, stat calc. This time we want to do exponential regression, so that's enter, and the exponential regression is r squared of 0.812. So far, linear is better. Then we're going to stat calc logarithmic regression, which is natural log regression. And that one has an r squared of 0.996. So this last one is the winner. And then we would want to write the model, write the equation of the appropriate model. So it would be Y equals 2.152 plus 2.704 natural log of X. And there's the model that fits that data the best. I know it fits the data the best because r squared is closest to 1 or negative 1. And then once I just identified that log was the one that fit the best, just write the model with the numbers in it. Okay, so I entered the information in my calculator under stat and edit. Now we're going to look at the r squared values of the line would be 0.927. And if I do stat calc exponential regression, that is 0.999. It's pretty good. And stat calc natural log regression is 0.765, which is clearly not the winner. The winner here is exponential, closest one to 1. So let's go back to stat calc exponential. I'll have to do that again so I can see the equation. And the equation is y equals 3.114 times 1.341 raised to the x. Okay, so real quick, just entered that information, calculated the r squareds of each one, found out the line fits the best, and wrote the equation provided by the calculator. Okay, so I entered the data into the calculator, calculated the r, found out natural log was the best fit, and wrote the equation from the calculator once I identified that fit was the best. Okay, so on 49 here, what we realize is that logarithms kind of follow the exponent rules that we're used to. So in this case, when I see two logarithms with exactly the same base being added together, I can combine them into a single logarithm whose arguments, the 3 and the x, are multiplied. Natural log of 3 to the x. On 50, I can bring numbers in front of logarithms up as the exponent, and then do the same thing. So the natural log of 5 squared would be 25, plus the natural log of x to the 4th, or in other words, as a single logarithm, the natural log of 25x to the 4th. Okay. When you subtract logarithms, you may divide the arguments. So the natural log of x divided by y is the condensed version of the natural log of x minus the natural log of y. Okay, so what we can do is we can put the 2 back up on top, call it the natural log of x plus 3 squared minus the natural log of 4, and then make it a single logarithm by writing it as the natural log of x plus 3 squared divided by 4. We may put the 3 up and the 5 up, so it would be the natural log of x to the 3rd plus the natural log of y to the 5th, and then we may put them together into a single logarithm of the natural log of x to the 3rd times y to the 5th. And the directions are kind of wordy here, but basically we're saying this is a single logarithm. Can it be expanded out into multiple logarithms? And so let's do that. It would be the natural log of 5 plus, since there's multiplication going on, the natural log of x squared. But even better than that, we can bring the exponent down in front and call this answer the natural log of 5 plus 2 natural log of x. Number 55, it would be the natural log of x squared minus the natural log of 4, but we could bring the exponent down in front and call this 2 natural log of x minus the natural log of 4. Simply on 56, bring the 5 down in front and call it 5 natural log of x. 57 would be the natural log of 3 minus the natural log of y. And 58, a lot of stuff going on here, but we'll just take it slowly. We've got a natural log of d to the 5th plus the natural log of f to the 2nd, and then minus the natural log of r to the 3rd. And then we can bring all those exponents down. So it'd be 5 natural log of d plus 2 natural log of f minus 3 natural log of r. Finding the answer to log base 7 of 15. The question is, what do you raise 7 to get 15? The answer can be found by doing the change of base formula, log of 15 divided by log of 7, or by using the log base feature of your calculator. Either one you use is fine. Log of 15 divided by log of 7, and that answer is 1.392, which it says evaluate to the nearest tenth. That's not very much, 1.4. Okay. Log base 3 of 81 is what do you raise 3 to get 81? And you can do that the same thing, log of 81 divided by log of 3. And the answer to the question is 4, which I kind of had a hunch about, because 3 times 3 times 3 times 3 does indeed give you 81. It takes 4 3s. Number 61 is what do you raise 10 to get 27? Well, I'm just going to find the log of 27. There's no reason to use anything other than the button log of 27 because we have a base 10 log on our calculator. And that is 1.43. The natural log of e to the 3rd. This is kind of a trick question because the natural log does not tell you what the base is because it's implied to be e, and we're trying to raise it to e to the 3rd. So the question is, what do you raise e to to get e to the third? And the answer to that, I think, is 3. Kind of a weird trick question. Now, if the e isn't there, clearly the natural log of 3 is not 3. Number 63 is kind of asking us a pretty simple question. When we don't tell you what the base is right here, it's 10. So the question is, what do you raise 10 to get 10 to the 5th? I think the answer to that's 5. 64, log base 4 of x equals 5 means that I must turn this into an exponential to find the answer. So 4 to the 5th equals x. And 4 to the 5th is equal to 1,024. Now on 65, I've got an exponential, and I need to use a logarithm to solve it. In this case, I'm specifically going to use natural log. Imply the base e, so the natural log of 15 is equal to x. The natural log of 15 is 2.708. 66. Let's get the exponential alone, and then we'll figure out what to do from there. So minus 10. 2e to the x equals 16. I still don't have the exponential alone. I got to get the 2 out of there. E to the x equals 8. And now what solves an exponential is a logarithm. And since the base is e, I'm going to think of it as the natural log of 8 that equals x. And the natural log of 8 is 2.08. Or 79. Okay? Number 67 is a base 10 log, so it's 10 raised to the 4th that equals x plus 6. 10 raised to the 4th is simply 10,000, but I would have to subtract 6, and so 9,994. Number 68 looks a little similar to that last problem, but it really is kind of different. I've got to get the log alone, so I have log of x equals -2, and then I can turn it into an exponential. The base here is understood to be 10, so 10 to the -2nd equals x, and 10 to the -2nd equals 100th or 100th, depending on how you write it, doesn't matter. Number 69, let's divide by 2 to get the exponential by himself. So e to the 3x equals 5/2. And then let's do the natural log of both sides, or turn it into a logarithm problem. In this case, the base is e, so we're going to natural log. The natural log of 5/2 equals the exponent 3x. So I'm going to find the natural log of 5 divided by 2, and then divide that answer by 3. And the overall answer for x turns out to be 0.305. And number 70 has a base of e, so I think I can turn this right into an exponential. A base of e raised to the first is supposed to equal the square root of x plus 2. I think maybe squaring both sides would get rid of a square root. Let's see here, get rid of that. Squaring both sides. So e to the first raised to the second would actually be e to the second. And squaring a square root gets rid of it. So now I can subtract 2 and find out what e to the second is. And subtract 2 from it. I get 5.39.